Hey, I'm Rage. Welcome back to my channel. Before we actually move on into our C++ series, we have to have a look on what is endianness. How does it affect us? And how does it work, right? What is it? How can we picture this? And in order to do that, let's not lose too much time and jump into some notes. So, in order to picture this, let's take our everyday numbers, because everyday numbers we're familiar with, right? So, when we deal with numbers in our everyday life, we have a set of digits, 10 in total, from 0 to 9, that help us to describe every number that we can imagine, right? And since we have 10 different digits, we can describe 10 different states at once. Therefore, our number system is called base 10 or decimal. I think so far we all agree. Let's start counting from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I thought we only have 10 digits. How is this possible? Well, when we come to the 9, we add a 1 to the 9, and actually what we do, we wrap around. We go back to the 0 in this sequence, right? But we have 1 left over that we somewhere have to put, right? So we carry it over. So we go and just place it in front of our 0, right? And we can count again on the sequence, 12, 13, and so on. Then we hit 19, and again on the right hand side we run out of digits. We wrap around again, we carry the 1, but in our second sequence we are still able to increase with the numbers or digits that we have, because 1 and 1 is 2, and for 2 we have a digit. And so on. Until we hit 99. Until we run also out of digits in the left-hand sequence. So what we do, we wrap around here, we carry the 1, and we also wrap around here, we carry the 1, and we have 100, because we have nothing that we can put the 1, so we just place it in front, and so on. If we now agree on one basic thing, that actually our numbers are not numbers, they are bytes, or they are combinations of bytes. Let's say that one sequence that we have is a byte. So, in order to go over 10, we have to introduce another byte that also only can contain at one time a 0 until 9. It can never have 2 digits, right? So, this means that if we have one of our bytes, or imaginary bytes, then we are able to say, okay, this byte can have 10 different states. Let's call this one byte A. And let's assume now we want to go over 10, right? As we do in everyday life. When we go over 10, we introduce a second sequence. So let's introduce a byte B. And let's say I want to describe a value of 10. I cannot do this with this byte A, because the 9 is the highest value that I can put. So I have to put a 9 or a 0 because I wrap around, and place the 1 into the byte B. And what we actually do when we write down numbers in this way, byte A and byte B, whenever we add a byte, then we add by 10 to the power of 1, right? So we have 0, in this example, 0 plus 10 to the power of 1 times 1 is 10, right? What if we want to go over 10, or we want to go over 99? Well, we introduce a next byte of our imaginary bytes and say, okay, I want to say 210, right? Then I place a 2 in the C byte, and what I do now is I don't multiply by 10 to the power of 1, I multiply by 10 to the power of 2. So I have 0 plus 10 to the power of 1 times 1 plus 10 to the power of 2 times 2, right? 0 plus times 10 to the power of 1 plus 10 to the power of 2 times 2. And this will be 0 plus 10 plus 200, and we can see we have 210. And interestingly, this 10 over here, right, is not because we have a base 10. Not in particular, it's because we define that we can only have 10 different states in our bytes. If we go now to our computer bytes, right, where we have binary, that means our only digits are 0 and 1, it would be quite inefficient to say one byte is only 0 or 1, right? Therefore, we have a layer more, we have bits abstractly. We usually cannot grab bits, right? So the smallest possible unit that we can work with in computer data effectively until we get down to hardware level is a byte. And a byte, because of efficiency, is a combination of 8 different bits, right? And if we have 8 different positions that can each have 2 different states, right? Then our range is 2 to the power of 8, right? Similar to what we have in here. The base to the power of how many positions we have. In here, it's 10 to the power of 1 is 10. In here, in our example before, we could have 10 different states. And in here, we could have 8 different states, so 2 to the power of 8, and this is equal to 256. If we now combine them with another byte, then we do the same, right? Times the number of different states that we can have. So we would say okay, we have here 2 to the power of 8, and here 2 to the power of 8. If we put 2 together, we have not 2 to the power of 16 possible states. And how much is it? 65,536. And we all know that this is the range of an unsigned int 16 integer. Therefore, we have the same principle in our everyday numbers that we have on bytes. As we now draw the line between our everyday numbers and bytes, let's go back to our everyday numbers and pick out some random numbers. Let's take the 15, the 111, and 1253. And let's divide them now into their parts. As we said that we have different containers or bytes that we can store them in, right? Where we have, like, on the right hand side, just times 1, we have 5, and we have on the left hand side times 10 to the power of 1, right? The more we go to the left. So this will represent a number 10. And in here we have the 1, remember, right? Right? So then we have a 10, and then we have a 100. And the same here, we have the 3, right? Times 10 to the power of 1, times 10 to the power of 2, and times 10 to the power of 3. And we see a pattern. It looks like that the biggest one is always on the left, and the lowest one is always on the right. And not enough. Because of that, if we now play around with our digits in each of these containers of these bytes that we imaginarily created, if we add 1 to the 5 and 1 to the 1, right? If we add the 1 to the 5, our number becomes 16, which in total, compared to 15, is an increase of 1. And for the 1 in the front, it will become a 25, which in total is an increase of 10. And the same, right? We have 112 plus 1, 121 plus 10, and 211 plus 100. And here the same again, plus 1, plus 10, plus 100, and plus 1000. So not only is the largest one in the front, it's also the one that affects the number the most when we change it. So if we now look up how endiannesses are defined, big endian and little endian, then we will see that big endian states that the most significant, let's say 1 first, and a little endian puts the least significant. One first. And the most significant one is the one that changes the number the most if we change it. And therefore, we can say that whenever we write down numbers, we write them in big endian. Because the biggest part of the number, we mention the first. Right? The 100. The 100 part, we mention first. We say 210 and not 0, 10, 200. Right? We don't write it like this. 0, 10, 200. No, we say 210. And it's clear now as well that if we do this in our everyday life, then it might just be a definition, right? It's not actually something that is driven out of some hardly technically requirements. It's just that for certain purposes, either is more optimal. That's all. That's the entire magic to it. So, in order to summarize this now, in the same way that for us in every day, it is more optimal to write our numbers having the biggest or the biggest part first. For computers to do certain things, it might also be either more optimal. And that's basically why we have big endian, little endian, middle endian, and mixed endian, and how they're all called. But mainly we have big endian and little endian, right? And that's the actually thing. There is no magic behind. It's just the way that, okay, if I put together my bytes into actual values, which one is which, right? If I write 1 and 2, do I have a 12 or a 21? That's it. I hope you liked it, and I hope to see you in the next time again. Have a good one.